Hi everyone, welcome back to your channel name. Today, we're diving into one of NASA's most mind-blowing achievements, hitting an asteroid a staggering 26 times further than expected. That's right, the DART mission, or Double Asteroid Redirection Test, achieved something truly out of this world. Buckle up as we break down what this means for space exploration and planetary defense. Let's get started. Asteroid impacts have always been a source of intrigue and curiosity. While rare, we still occasionally hear about asteroids entering Earth's atmosphere in news reports today. They've also captured our imaginations as the central theme in countless disaster movies. But why are they so compelling? Perhaps it's because these space rocks are believed to have caused the mass extinction event 66 million years ago, wiping out 76% of all species on Earth. Was that event just a fluke? Or could it happen again? And if a massive asteroid were hurtling toward Earth, would we have the technology to stop it? Could humanity survive such a catastrophe? I'm Alex McColgan, and you're watching Astrum. In this episode, we'll explore the DART mission, humanity's groundbreaking attempt to alter the course of an asteroid, and take a proactive step in protecting our planet from potential extinction-level threats. Asteroid impacts have shaped the Earth's history in profound ways. In the chaotic early days of the solar system, one of the most significant impacts likely created the Moon, when a planet-sized object named Theia collided with a young Earth. These violent collisions may have also delivered water to our planet, filling our oceans and making life possible. However, these impacts haven't always been a blessing. Over time, asteroids have caused massive destruction, including several mass extinction events. The most famous of these is the Chicxulub impact, which left a massive crater and likely triggered the extinction of the dinosaurs 66 million years ago. Interestingly, there's a clear relationship between the size of these objects and how often they collide with Earth. While small impacts happen frequently, larger, more devastating collisions are far less common. Still, the question remains, could we prevent a major asteroid impact if one were heading our way? Let's find out. Earth is constantly bombarded by objects from space, but fortunately, collisions with large ones are incredibly rare. As the solar system ages, such impacts have become even less frequent. Why? Because when asteroids collide, they often break into smaller pieces or merge with larger celestial bodies like planets. In fact, Earth gains about 15,000 tons of material every year from meteors entering its atmosphere. Surprising, right? Impacts happen far more often than most people realize, but the vast majority go unnoticed. The meteors we know as shooting stars are typically tiny, ranging from sand grains to small pebbles just a few centimeters across. These burn up spectacularly as they streak through the atmosphere, creating beautiful displays of light. So, how many meteors do you think hit Earth's atmosphere every single day? The answer might shock you. A staggering 25 million. But don't worry, the average meteor is only about 40 centimeters across. On any given year, the largest meteor might measure around 4 meters. Every century, Earth encounters one that's at least 20 meters wide. These objects are more substantial, and some even survive their fiery descent through the atmosphere, landing on the surface. When that happens, they're no longer called meteors, they're meteorites. For a meteor to survive the intense heat and pressure of entry, it usually needs to be relatively large. Even so, what reaches the ground is often only the size of a brick. These space rocks sometimes create dazzling trails across the sky, known as fireballs, with vibrant colors lighting up the night. And every 2,000 years or so, a meteor comes along that's even bigger. But just how big and what happens when it does? Let's explore. Imagine a 100-meter wide asteroid hurtling toward Earth, slamming through the atmosphere with unimaginable force. The result? Devastation, not just from the impact itself, but also from the powerful airburst that follows. Now consider objects even larger, over 10 kilometers wide, big enough to threaten entire civilizations. These are the stuff of apocalyptic scenarios, but thankfully, they only appear once every several million years. The good news? The odds of anyone alive today witnessing such a catastrophic event are astronomically low. Even better, these massive objects are easier to detect. Scientists are confident that they've identified nearly all nearby asteroids of this size with a very high degree of certainty. But what about smaller, harder to spot meteors? These still pose significant risks, especially on a local scale. Take the Chelyabinsk meteor of 2013, for example. When it exploded over Russia, it injured 1,500 people and caused widespread damage, shattering windows and structures across 6 cities. The shockwave damaged 7,200 buildings, and while no fatalities occurred, it was a stark reminder of the potential danger. Now, imagine a similar event over a densely populated city. The devastation could be catastrophic, with thousands of lives at risk. That's why detecting and preventing asteroid impacts is more than just a scientific challenge. It's a global priority. The key to safeguarding our planet lies in early detection. By finding and tracking potentially hazardous objects in space, we can prepare for and even prevent disasters. And we're making incredible progress. Over the past 2 decades, scientists have identified more than 20,000 potentially dangerous asteroids, using advanced technology to improve detection rates like never before. Every week, scientists add around 30 new asteroid discoveries to their catalog. Thankfully, most of these space rocks have harmless orbits, posing no threat to Earth. But what if we discovered one heading straight for us? What could we do to prevent a disaster? That's the question NASA set out to answer with its groundbreaking DART mission, the Double Asteroid Redirection Test. This ambitious project was a collaboration between NASA, the Johns Hopkins Applied Physics Laboratory, and international partners from Italy, Japan, and the European Space Agency. Its mission? To test whether humanity could redirect an asteroid's path by crashing a spacecraft into it. Before DART, there were many creative ideas about how to stop an asteroid on a collision course with Earth. One possibility, if we had enough warning and the asteroid was small enough, involved using a spacecraft as a gravity tractor. By flying alongside the asteroid for an extended period, the spacecraft's gravitational pull could nudge the asteroid just enough to shift its orbit away from Earth. It might sound like science fiction, but in 2015, NASA confirmed that this method could actually work. Then there's the more dramatic and popularized idea of using nuclear weapons. Thanks to movies like Armageddon, many people imagine detonating a nuke to shatter the asteroid into harmless pieces. But here's the problem. Asteroids aren't as solid as they seem. They're often loose collections of rubble, not solid rocks, and blowing one up could leave behind a swarm of dangerous fragments still hurtling toward Earth. In other words, nuking an asteroid might not be as effective as Hollywood makes it seem. That's why missions like DART are so critical. They represent humanity's first real-world attempt to solve a cosmic threat, not with explosions, but with precision and innovation. Let's explore how it all unfolded. If a nuclear explosion shattered an asteroid into pieces, the result might be even worse than the original threat. Instead of a single bullet heading toward Earth, we could end up with a deadly shotgun spray of fragments, each capable of causing significant damage. This unsettling scenario is one reason why alternative strategies have been explored. One such idea involves using reflective mirrors. The concept is inspired by comets, which often outgas when they heat up near the sun, creating natural propulsion. A spacecraft equipped with mirrors could reflect sunlight onto a specific spot on an asteroid, heating it up and triggering a similar outgassing effect. This could cause the asteroid to gently push itself off its collision course, with Earth using its own released gases. However, the team behind DART decided to focus on a simpler, more direct approach, impacting the asteroid itself. The goal wasn't to blow it up, but to use the sheer force of a collision to nudge it off its deadly trajectory. This method, known as the kinetic impactor technique, was chosen for its straightforward execution and proven track record. It had already been successfully tested on a comet in a previous mission. Once the approach was decided, the next challenge was selecting a suitable target. Scientists chose Dimorphos, a small asteroid just 160 meters across that orbits a larger asteroid, Didymos, in a binary system. This pair of space rocks had been under observation for years. Didymos was first discovered in 1996 by the Spacewatch project in Arizona, while Dimorphos was identified later in 2003. Dimorphos was the perfect candidate, small enough to test the concept, but large enough to demonstrate the potential of this method for real-world threats. With the plan set and the target identified, DART was ready to make history. Dimorphos, the smaller companion of the 780-meter-wide Didymos, orbits its larger neighbor at a distance of about 1 kilometer, completing a lap every 11.9 hours. Together, the two asteroids orbit the Sun once every 2.1 Earth years. In October 2022, this dynamic duo made its closest approach to Earth in nearly 2 decades, coming within 10.6 million kilometers, a perfect opportunity for NASA's DART mission to visit. This relative closeness made Dimorphos an ideal target. It was close enough to reach without excessive travel time or resources, but far enough to pose zero risk to Earth even if the mission altered its orbit. Scientists were confident that no matter the outcome, Dimorphos wouldn't endanger our planet. With the target locked in, NASA set out to design the perfect spacecraft for the job. Unlike the complex probes we often associate with space exploration, DART was a straightforward machine. About the size of a refrigerator and weighing just 610 kilograms, it was dwarfed by Dimorphos, which weighs an estimated 5 billion kilograms. But DART didn't need size or frills, it just needed to hit its mark. At the heart of the spacecraft was DRACO, short for Didymos Reconnaissance, and Asteroid Camera for optical navigation, a high-resolution camera that served as DART's eyes, helping it navigate autonomously to its target. Alongside DRACO were other sensors and systems that ensured the spacecraft could adjust its course as it closed in on Dimorphos. Adding to the mission's innovation was a secondary companion, LICIACube. Built by the Italian Space Agency, ASI, this small CubeSat was designed to separate from DART before impact. Its role? To capture close-up images of the collision and its aftermath, providing valuable data on how the asteroid's trajectory and surface changed. In a poetic twist, DART and LICIACube, a binary spacecraft team, were visiting a binary asteroid system, making this mission a perfect pairing of science and symbolism. With everything in place, the stage was set for a historic encounter. 15 days before the historic impact, LICIACube separated from DART to prepare for its unique mission, capturing the moment of impact and the aftermath. Equipped with 2 optical cameras charmingly named LUKE and LAIA, a delightful nod for Star Wars fans, this small CubeSat weighed just 14 kilograms and measured about 30 centimeters long. Using its own autonomous navigation system, LICIACube flew by the asteroid system, ready to document history in the making. Meanwhile, the DART spacecraft was on its own, operating entirely autonomously during the final stages of the mission. Why? Because at such vast distances, the delay in communication between Earth and the spacecraft made real-time instructions impossible. DART needed to locate Dimorphos, choose the perfect impact point, and precisely steer itself, all without human intervention. This is where SMART-NAV, small body maneuvering, autonomous real-time navigation, played a crucial role. This advanced optical navigation system distinguished between Dimorphos and its larger companion, Didymos, locked onto the smaller target, and guided DART to its final destination, all in the last hour before impact. DART's journey began on November 23, 2021 when it launched aboard a SpaceX Falcon 9 rocket. Over the next 10 months, it traveled across space toward its target. In the critical 4 hours before impact, at a distance of 90,000 kilometers, DART's internal navigation system took full control. Then, with 90 minutes left, ESM-ART nav kicked in, refining the spacecraft's trajectory for pinpoint accuracy. As DART approached 24,000 kilometers from Dimorphos, the asteroid finally came into view through its DRACO camera. At first, it was just a faint smudge, taking up only 1.4 pixels, but this humble image marked a monumental moment. For the first time, both Dimorphos and its parent asteroid, Didymos, were visible together, setting the stage for the final act of this daring mission. As DART streaked toward Dimorphos at a blistering 22,000 kilometers per hour, it captured one final, unforgettable series of images. In its last moments, the spacecraft brought its target into stunning focus. Just 3 seconds before impact, an image revealed Dimorphos in remarkable detail. You could clearly see its composition, a loose pile of rubble, a cosmic leftover from the birth of the solar system. This snapshot was more than a photograph. It was a window into the asteroid's chaotic origins. Then came DART's final fully transmitted image, taken from just 12 kilometers away and only 2 seconds before impact. The level of detail is astonishing, with a resolution of roughly 3 centimeters per pixel, revealing the intricate texture of Dimorphos' surface. And finally, DART sent back its last image, an incomplete one. The transmission was cut short as the spacecraft met its spectacular self-engineered demise. Strangely, this partially transmitted image is perhaps the most powerful of all. Its abrupt incompleteness freezes a moment of sheer drama, a poignant reminder of the instant when DART fulfilled its 17.5 million kilometer mission with breathtaking precision. This achievement wasn't just about engineering. It was a triumph of human ingenuity and determination. Frames appear slightly blurred, a result of DART's ion thrusters causing vibrations in its camera. Yet, even with these minor distortions, the sequence captures the heart-pounding approach to Dimorphos, culminating in one of the most ambitious and successful planetary defense experiments in human history. The sheer speed of DART's approach is mind-boggling. It successfully struck an object only 160 meters wide, while traveling at 22,000 kilometers per hour. That level of precision is astonishing. The fact that some of these images are so sharp is nothing short of miraculous. Imagine how quickly the onboard camera had to adapt to a rapidly growing target as the spacecraft closed the distance in mere seconds. But let's get to the question you're dying to have answered. Was the mission a success? The answer is a resounding yes. In fact, the results exceeded expectations by a wide margin. NASA had set a modest benchmark for success, a change in Dimorphos' orbital period of at least 73 seconds. Instead, DART's impact achieved a dramatic shift, shortening the moonlet's orbital period by a staggering 32 minutes from 11 hours and 55 minutes to 11 hours and 23 minutes. Even accounting for a margin of error of plus or minus 2 minutes, this is 25 times the original goal. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.